Hey everybody, this is going to be the study guide for Unit 8. Before I get started though, just make sure you take note that this is for BC only, the BC test only. So if you've decided to switch to just taking the AB test, you can ignore this video. These topics are all on just the BC test, not on the AB test this year. Okay. So this is Unit 8. This is more applications of integration. And so in the previous video from Unit 6, that was talking about Riemann sums and things like that. That's the introduction to integration. Unit 8 is continuing those applications of integration and finding the area under the curve and using the integral to do different things. Here at the top we have a couple of formulas for average value of a function. This is very easy to identify in free response problems. The part of the free response problem will just straight up ask you what is the average value of whatever function. So if that function's letter is g or h, g of x, h of x, or something else, it'll say what is the average value of h of x. And you would look for wherever the function h is, and then you would apply this formula here. So I'll just leave a general average value of f of x, but don't get that confused. The f of x could be some other letter too. It could be some other function. But the average value is the area under the curve from two points A to B. So it also asks you the average value from point A to point B. Whatever those numbers are, those are your bounds. The average value of the function is the integral, so the area under the curve divided by the distance between the x values of your bounds. So it's kind of like an average. You total everything up and then you divide by how many things there were. So here we want to do 1 over, this represents the divided by b minus a. And there's your average value formula. 1 over b minus a times the integral of the function that you're finding the average value of. The second formula up here is the arc length formula. And this is if you wanted to measure the length of some curve and find those the units of some part of a curve, you'd use the arc length formula. And so this is kind of the equivalent of putting a piece of string on the function, however it's curved, and then cutting it at point A and point B. And then if you were to measure the length of that line or that piece of string that you have cut, this is the arc length formula. The way you find the arc length formula is you still use an integral from A to B. It'll give you those bounds. And this formula, there's a derivation for it. There's a place where this comes from, but for the AP test, it's not pertinent. You just need to know the formula itself if this does come up. It's going to be 1 plus f prime of x and the square root of all of that dx. And since you'll have your calculator on your test, you'll be able to just punch this straight in, and if it asks you that, and you would find the arc length using this formula right here. The one thing you would need to do, a little piece of work here, is if you're given the original function, you would have to take its derivative. That's about it. But the derivative goes right here, 1 plus that, square root it from A to B. That's your arc length. Okay, the next applications of integration were area and volume. And this is finding the exact area using the integral. So there's two ways that we could find area. You could find the area with respect to x or with respect to y, depending on the way the functions look. And so if you're confused on how to decide between if it's with respect to x or y, the way you determine this is you look at your two functions, and the right side and the left side, if they're parallel, these bounds a and b, the bounds a and b are parallel on either side. So this is a top minus bottom. This is with respect to x, because I can always draw a line from the top straight down to the bottom all throughout this interval. And if it's right minus left, that means your upper bound and lower bound are parallel to each other. So you can kind of see the parallel parts that tell you whether it's with respect to x or with respect to y. And so the integral for an area between curves with respect to x is going to be top minus bottom, and your bounds are a and b, which are those x values right there. So actually on the integral, I'll put x equals a and x equals b, because those are x values. They're on the x-axis, a and b are. So just know that this is in terms of x, because everything is in terms of x. Your bounds, your functions, so let's say the top was f of x and the bottom was g of x. It will be f of x minus g of x dx at the end. So notice how everywhere in this integral you see x's. F of x, g of x, dx, x equals a, x equals b in your bounds. All in terms of x. This is a top minus bottom. For an area with respect to y, it's all the same, except it's just right minus left, and everything is in terms of y. So we'll have the same type of integral again, area, and this time instead of x equals a, it's going to be the bottom bound y equals a to the top bound y equals b. So I put y equals there because these a and b values are y values. They're on the y-axis. The integral is, instead of top minus bottom, it's right minus left. So let's say the right side was the function f. Then I would put f of y. So now if you were given an equation, you would have to solve that equation to be x equals all the stuff in terms of y. And minus, and then let's say the left side was g of y. Close the brackets, dy at the end. So notice how everything here is in terms of y. Okay, so there's area between two curves. Now let's talk about volume with disk method. With a disk method, you have an axis of revolution and you have one other function, or one other graph. And that graph is being revolved around this axis of revolution. And so the way we do this is, we think about when you revolve this function, if you take one point and revolve it around, you've created a circle. So pi, this whole thing is r. The radius of the circle is the distance between the function to your axis of revolution. That's the radius. And then squaring that will be pi r squared, creating this circle. And if you integrate that, it takes all of the circles in that interval, whether they're really small or really large, it takes the areas of all those circles and it adds them up, making this volume. So this first one isn't when your volume is in terms of x, and then this bottom one is if your graph is in terms of y. Okay, same principles as the first two boxes at the top, so I won't go back and explain that, but here's in terms of x, here's in terms of y. So it could be either one of these depending on the way the graphs look. Okay, so, and then this axis right here, since this axis is, since this integral is in terms of x, that means your axis of revolution is being revolved vertically like this. Okay, so I'll just draw an arrow. Let me use a different color. This axis right here, your axis of revolution is going to be some y equals number, like some horizontal line. So let me actually just write horizontal. So I'll just draw a little picture like here. Here's your horizontal axis and you're revolving vertically like this around it. And so that means if it's in terms of y, this is a vertical line. The axis is a vertical line. The axis is vertical and you're revolving this way around it. So that means that your axis was vertical and you're revolving around it kind of like this. Okay? I'll put, let me be as specific as I can. Axis is, just so there's no ambiguity or confusion, axis is horizontal or axis is vertical. Okay, volume with the washer method. Essentially the washer method is two disk methods. As you can see, there's still one integral, but if you notice there's there's an r squared here, and there's another r squared here. And that pi can be distributed to both of them. Since it is an integral, you could do pi r squared for the first one minus pi r squared for the second one. It could be two integrals technically, or you could just write it as one big integral like this. Either way you'll get the right answer, but it's two disk methods essentially. Washer method is two disk methods. You're integrating a larger disk, a bigger radius, and then there's another small radius in there that you're subtracting out of that, and it creates airspace inside of it. And I'll work a couple of examples of both the disk method and the washer method so you can see the difference. But so these are the two formulas. The only thing you'll need to know is that what the order is. F of x is always going to be further away from the axis because this is the larger radius. G of x is always going to be closer to the axis. So for both of these, f of x and f of y, I'm going to write that that's going to be further from the axis. So I'll put the word further, whether it's in terms of x or in terms of y. The first function you put minus the axis is always the one that's further away. And the second one, g, is the one that's closer to the axis. Okay, so that's what I'll put there about that, just so there's a lot of clarity in these formulas and when to use them. Okay, so there's the washer method, and then here at the bottom we could also have volume with cross sections, which is not revolving around an axis, but it's using the graphs as the base of a solid, and you're out of the page you're lifting out some cross section. You can think of how bread is made. You lay the batter or you lay the dough flat, and then when you bake it, the dough rises, it goes upward. So you're thinking about you're baking this piece of bread or this loaf of bread and it's rising. Now, depending on which cross section is asked for, your bread is rising in a different shape. So it could be a square, rectangle, triangle, or semicircle. That's what the AP tests on these four types of shapes. So if a square rises out of the page, it's just base squared because the area of one square is side squared, and you're integrating from A to B. So now you're taking all of these squares in some interval and you're adding them all up. The integral is adding all of these areas up and making a volume. Rectangle is base times height, triangle is 1/2 base times height, and then semicircle is pi r squared divided by 2. And so they could be in terms of dx or dy, dx or dy, dx or dy, once again depending on the orientation of the graphs, as I mentioned earlier. But I'm also going to try to work do one video for each of these examples so you can see free response problems and how they're worked in terms of these problems right here. Okay. As always, if you have questions, please let me know. And then lastly, once again, remember this is a study guide just for the BC test. It's not going to be tested on the AB test. So if you're taking the AB test, then you don't need to worry about this information. This unit will not be on the AB test.